-1. All right, hi. Welcome back to Math 234. I am still your host, Steve Dragoo. Today, we're starting an entirely new chapter. So for at least the first couple of lessons, there aren't any pre-class videos that you'll need to watch. So there wasn't one for this one, because we're just going to go over all of it today in class. And then next lecture, there's also not a pre-class video. That'll be for iterated integrals, which is totally different from double integrals, I swear. But these next couple of topics, again, I think it's kind of a new, fresh start we're getting into for this exam 3 content. Also, exam 3, I think is it the only test that's only on one chapter? No, I have to take that back. We do one section of chapter 16 right at the very, very end. But it's the easiest section out of chapter 16, for what that's worth. So almost all just in chapter 15, where we're going to look at multivariable integrals, which are somewhat different from the line integrals that we just did, right, as like our last topic before exam 2. But these I think are going to be maybe even easier than that, or at least they're going to start that way for like the first 3 lessons. Then we're going to get into polar coordinates and I'll make a liar out of myself. But anyway, double integrals. Let's get right into it. So, as the name might suggest, it's 2 integrals, or at least its symbol, as because today we're just going to be interpreting this thing as symbolically what is a double integral. We'll worry about actually calculating one of them later. But it's an integral with 2 integral signs, hence double integral. We do 2 of them. Practically speaking, once we actually start evaluating them in a significant way, we will just be doing 2 integrals in succession. So we'll probably do one for x, and then we'll do one for y, kind of the same way that we do our partial derivatives, where we have one for x and we have one for y. But again, today we're just going to try to understand it symbolically and figure out what it means without actually having to calculate something, or without. Again, I'm going to make a liar out of myself. We won't compute them directly. We'll look at sort of dancing around computing them directly. And then we'll do the real calculation on Wednesday of next week. Right, so again, double integral, it's got 2 integral signs. And also, I want to call attention to this guy right down here. That R that I'm putting down at the bottom of this double integral sign. Because as you might have noticed over the last couple of lessons, every time we did a line integral, I put a little C down at the bottom of the integral sign, at least when I was writing it in its general form with like the ds included. Now, we're going to be writing an R down there instead of a C. To sort of explain what those things mean, whatever I'm writing down at the bottom is just telling me the domain of my integral. When we did integrals back in Calc 1, we were pretty much exclusively integrating over intervals. Typically, they were x intervals, and they went from some smaller value a to some larger value b. So we just always wrote in from a to b. But if we're just generalizing the space that we're integrating over, we might use a letter to represent what that space is. So we were always using a C for curve, meaning that was a one-dimensional curving line somewhere through 3 space, but again, denoting that our integral happened over a curve. Now we're integrating over regions. Our domain is going to be some kind of an area. So we're going to use R for region, and that's the new thing that we're integrating over. Yeah, very, very general and somewhat dry. But again, you'll probably notice that I'm writing in some letters down at the bottom of my integral signs. And again, it's just to signify the domain I'm integrating over. But to continue taking things back to Calc 1, I want to start trying to understand what this double integral is. And the way that we're going to do that is with the same kind of Riemann sums that we first started trying to do regular integrals with back in the day. So whereas in a Calc 1 integral, we were looking at the area under some curve, and we said that was going to be equal to the integral, and we'll approximate that with some rectangles. We're going to say that a double integral is the volume under some surface. And we're going to, again, approximate it with rectangular boxes. My emphasis got all screwed up there. Rectangular boxes, right? We're going to use boxes instead of rectangles because now they need to be three-dimensional shapes. But we still want to come back to the idea of some rectangles. So if I just kind of glance over here to the right at some of the diagrams that I came pre-prepared with, if that blue shape is my surface, it's some function z equals f of x and y. So z, again, function of x and y. My domain is just going to be the rectangular region that's projected down into the xy plane. Again, that's what my r is going to be that I spent a bunch of time talking about. The solution, or the answer to the double integral over that region, is the volume that's underneath that blue surface. And again, we're going to start approximating that with a bunch of rectangular boxes as sketched right over here, just below that. So if I look at the region that I'm going to start looking at for this integral, maybe I'm just going to break down this box right here where the r is. And then that's the shape that I'm blowing up over here on the right, where f of 2, 1 would be the function value at that point. All right, so I just trace that point up to the function, and that'll be the height of my rectangle. Right, if I'm looking over here at trying to assemble what my rectangular boxes are going to look like, they're going to have some standardized base area. In the example I'm doing here, that's going to be 1 by 1. We'll go over the whole example in a second. But it's a 1 by 1 rectangle that's got to have some height to it in order to get a volume of a box. And the height, just like we did back in Calc 1, that height is going to be the function value somewhere within that rectangle. Also point out that this rectangle is a square, but in general, they'll be rectangles. So if I want to get the volume of just this box alone, it looks like it's 1 times 1 times, well, if I just evaluate 2, 1 in my function, 6 minus x minus y, that's going to be 3. So 1 times 1 times 3. And if that's the box for just that one subrectangle, I'll just add up all 6 of them and have my approximation. So let's build that up. So finally to the example, using 6 rectangles of width and length of 1 to approximate volume under this function in the region R shown below using a top right sum. So that means within each of my 4 rectangles, I'm going to use the upper right corner to figure out my value should be. What other color do I want to add in here? How about green there, maybe. Let's put a yellow one down. Oh, what color have I not used? Oh no, yellow can go up here. Magenta we haven't used yet. Cool. So I'm going to pick those upper right corners for the different boxes. This just give them all some labels. A, B, C is in blue. D can be this one. E and F. All right, so those are my 6 rectangles. And again, my problem is asking me to use a top right sum. So, back in Calc 1, when we were doing these Riemann sums, we'd have like right-hand sums and left-hand sums. Well, now that our base region is a rectangle, right and left isn't quite enough anymore. So now we'll just, for the basic options, we'll look at the 4 corners, upper right, upper left, lower right, and lower left, to generate where we're going to collect our function values from. But also, I don't want to spend too much effort trying to break down these different Riemann sums because we're going to do like 2 examples and then completely move on from this topic for the rest of ever. So, top right sum, let's go generate some of this stuff. I am going to need some function values. I'll want f of, let's see, that'll be 1, 1, 1, 1. for A, f of 1, 2. For B, f of 2, 1. And f of 2, 2. And then f of 3, 1. And f of 3, 2. So writing those somewhat in order. And I already know that the purple one is going to be 3. So I computed that one over to the right. But if I just go through and find values for the rest of these things, let's see. F of 1, 1. I've got 6 minus 1 minus 1 is 4. To box number B, f of 1, 2. 6 minus 1 minus 2 is 3. Then also 6 minus 2 minus 1, the purple one we said was 3. 6 minus 2 minus 2, the green one, is going to be just 2. Let's go down and do pink. 6 minus 3 minus 1 is also 2. And finally, 6 minus 3 minus 2 is 5. That was yellow. Nope. 6 minus 3 minus 2 is 6 minus 5, which is 1. Yeah. Yeah, saw a couple of looks out there. So, yep, figured that one out all on one, kind of. But now I've got all of my function values. I just need to add them all up. And I'm gonna do some things down here. First off, I'm going to say that the double integral over my region R of f of, well, I know what f is now. It's 6 minus x minus y. dA is approximately equal to the volume of all of these boxes added together. Which, for that first one, is going to be 4 times its base height, which is, or its base area, which is 1. Plus, I'd do 3 times its base area, which is 1, 1 by 1. Plus, I'm going to keep adding all of those up. Every single one's got the same base area because they all have the same rectangle of 1 that they're above, which means I could factor it out. So I'm going to just do that real quick. Well, let's pull you out here. And then just add up all the heights. So plus 3, plus 3, plus 2, plus 2. And finally, plus 1. Right, all of those heights all added up, multiplied by the same base area of 1 is 15, I think. If I just start on the outsides and add in, I have a pretty nice sequence. 4 and 1 is 5, 3 and 2 is 5, 3 and 2 is 5 again. So 15, though I probably don't need to teach you guys how to add 6 whole numbers together. But maybe you could teach me because I seem to be really, really good at it. Right, so I got that my volume's about 15. Or rather, the volume of all the boxes is 15, which means that the integral, the double integral, is approximately 15. So if we wanted to formalize that idea, hey, look, it's a Riemann sum. It's the limit as n goes to infinity of the sum from I equals 1 to n of the function f of xi star, yi star times delta a. Where we have these super fancy xi stars and yi stars, and those are going to correspond to the x and the y values in the I subrectangle. Yeah, we're gonna go with that's a word. Practically speaking, though, So like if I call them the subrectangles, that means that each of my subrectangles is the thing that I am indexing over rather than the individual x and y values. Which means if I ever actually want to calculate one of these things the hard way, which I guess we're going to do in like 1 second, I'm probably going to need two sums in order to do that. One for the x values and one for the I values. So I want to break down my index into x and y values. But at least for this format, we can condense it into a single sum where we're indexing over the total number of rectangles instead of just the x and y indices. But anywho, yeah, so there's going to be our Riemann sum. And here's kind of what it looks like if I'm doing it over volumes. The figure on the right shows a whole bunch of rectangular boxes that I'm all going to add up and say, hey, look, the volume's about that. You can probably get the sense that if I take the number or the limit as the number of boxes goes to infinity in a good way, this thing will smooth itself out and end up looking like the surface over on the left. But the left side also breaks down, where each of those individual rectangular boxes are coming from, kind of how they get generated. And we just, take a height based on the box that we've projected down into the XY plane. And we're going to add them all up. It's going to be really, really fun. I promise. Also, I'm sure I'll make this comment again later, but I'm thinking about it right now, and I know that I just talked about it in line integrals. Our new differential is dA, right? As opposed to ds is the new one that we just introduced, which was supposed to be a small incremental move along a curve S. Was it ds? That was our differential. It tells us how the curve is moving, and we have to translate that back into like a dt or something that we know how to integrate. dA then is going to be a small incremental change in the area, which probably means when we're doing an integral, we'll need to break dA down into one-dimensional movements. But that's more of a preview of what we're doing next time. So moving on to the next bit. Let's try like one more Riemann sum before we call it a day. Or at least call it done with Riemann sums forever. So what do we have? A function, x times 1 plus y. Given by the inequalities, x is 0 to 1, y is 0 to 2. Notice it's going to be that rectangle that I sketched out over on the left, given that I don't apparently care about my axis labels. That'll be fine, though. We're going to choose the subdivision of D, D again being the region that's on the left, into squares with side lengths of 1, and we're going to use sample points of the Riemann sums in the top left corner of each square to approximate the integral. So I took the liberty of already, again, making those two squares. And if I look at their upper left corners, upper left would be right here, right? That way. Hey, stop that. Upper left is there, and upper left, stop it, is there. Maybe I should just zoom in. Yeah, there we go. All right, fine. We can do it that way. So those are my two upper left corners, and I just need to go get function values there. So f of, in that upper left, that'll be 0, 1, which is going to look like 0 times 1 plus 1, which is 0. And I also want to get f of 0, 2. You can probably see where that's going. This is 0 times 1 plus 2, which is also 0. Let's pretend like I didn't already know that. I also need to go get my delta A value. Delta A, it's just the area of each of those squares, which is 1 times 1, or just 1. So then my double integral, I'm kind of beating a dead horse here, I think, because I'm guessing you already know the answer. But the double integral of x times 1 plus y dA is approximately 0 times 0 times 1. Nope, 0 times 0. Let's try that again. 0 plus 0. There we go. Times 1. It's going to still result in the same answer, though. I get 0 no matter which way I slice it. So, kind of a boring Riemann sum, but that's okay because it's nice to have one or two easy examples. Because the next stage of this Riemann sum journey that we're on is to compute it out the hard way. So, same thing, same function, same rectangle. Formally compute that integral, that double integral, using two Riemann sums. So here's where we need to recall some stuff out of Calc 1. So if you really hated this section, just close your eyes for the next 5 minutes and it'll be over with soon. But we're gonna break down all of the individual pieces of a Riemann sum and then try to add them all up. So, as you might recall, when we're looking for delta x from back in Calc 1, we're really just going to have to do this twice. We had to take the length of our interval, which is b minus a, divide it by the total number of rectangles that I'm going to use, which is going to be n, to give the length of each rectangle. Then I said that each individual x value, which we'd call xi, because I need to index through all of the x's as I go from A, my starting point, all the way down to B, which is my ending point, is going to be A plus I times delta x. I is my index. It just counts up from 1 to n, wherever my stopping point is. Delta x is how much I'm going to change my x's by, so I go up a little bit each time until I get to my end point. All right, if I add up, a plus n delta x being my final n value, or my final I value, I'm going to get to b, right? The idea is that xi traverses from a all the way to b by the time I get to the end of my index. And then the calculus part is taking a limit of that thing. But let's slow down on the calculus part for a second and just figure out what these values should be. So we are going to need a delta x for this problem, which is going to be 1 minus 0 over n, or just 1 over n. 1 and 0 come from the fact that x is between 0 and 1. Right, that's my x interval, 0 to 1. Now that I have delta x, I can go get an expression for xi, which is going to be 0, because I'm starting at 0. A plus I delta x. So this is 0 plus I times 1 over n. And then I got to go do the same thing for delta y, right? Because I need to index both of my variables because this is multivariable calculus. Yeah. All right. One of these days I'll stop doing that. But it's not today. 2 minus 0 over n, or just 2 over n for my delta y, keeping in mind that y goes from 0 to 2 as opposed to x, which just went from 0 to 1. I can also go get my yi's, which will be 0, because again, I'm still starting this thing at 0, plus j times 2 over n, because now I need a second index to talk about my j's. I'll be indexing them separately. So we did say we wanted two Riemann sums, and the letter in the alphabet after I is J. So that's where I got my second index. Notice that these are not the same I, J, and K that we would use for the basis vectors. They're just indices. Finally, I am going to need probably a delta A in here, which if I just go down to another diagram that I have pretty prepped. So same rectangle, except mine is a bit more square shaped for no particular reason. Uh, Axes are not drawn to scale. Delta A that goes inside of that double Riemann sum really should be the area of each individual rectangle that I'm going to be summing over. Right? Because ultimately this needs to be that rectangular area multiplied by the height to get each of the boxes that I'm trying to add up. So I need an expression for it. And if I just look at just some generic rectangle there in the middle, I can see that each of those rectangles should have an area of delta y times delta x. Right? The little incremental change in x multiplied by the little incremental change in y, that gets me my area delta A. Also suggests where dA is gonna go, because if delta A is delta x times delta y, then dA after some, magic calculus should probably transform into dx times dy. That's kind of where the delta A is coming from. But again, that's just a highlight for next week. But okay, I digress again. Yeah, delta A should be delta x times delta y. So let's go write down that expression up here. Delta A, we need it next. It'll be 1 over n times 2 over n, which is 2 over n squared. And now we've got all of our individual pieces. So let's try and build this double Riemann sum somewhere. All right, so we want what exactly? The limit as n goes to infinity of the double sum, one for I, one for j, both of them go to n. And we're going to look at f of xi, yj times delta a. That's the thing that we gotta compute. In each of these sums, delta I again is the area of those rectangles. The function value f of xi, yj, that's just the height of the rectangle at whatever point that is somewhere inside each of these rectangles. And we can write expressions out for all of that stuff. So let's just go do that. This is the limit as n goes to infinity of a double sum. One from I to n, one from j to n. And we're looking at what? X times 1 plus y, right? Which really means it's xi times 1 plus yi. Xi was I over n. And y was 2j over n. And then this thing gets multiplied by 2 over n squared. 2 over n squared. And we get to do all of that. And look how much space is left to do all of that math. If I were to highlight a couple of elements out of this sum, things to recall. N on the inside of a sum is really just a number, right? N is not related to the index, aside from it being the maximum value of the index, but it doesn't matter to the sum itself. as far as the sum is concerned, n is a fixed value. It's not until I take the limit, which happens after the sum, that n ends up becoming kind of a variable. Meaning, I can always factor n's out of the sums that they're inside of, because the sum will treat n as just a fixed value. The only variables, as far as the two sums are concerned, are I and j. And since they're being multiplied together, I can separate out my two sums into a product of sums. Again, only the i's and the j's matter. And a couple of things that I'm looking at that I think I might need to recall. Put some ellipses over here. I can see that I am going to need to know the sum of j or I. I just need to recall the sum of an index as it goes from 1 to n. So that's, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. And well, you get the idea. I probably could have stopped well before that. But that thing should get resolved to n times n plus 1 over 2. I can also see, looking on the inside of that y sum, that I'm going to ultimately need to sum up just the value 1 from 1 to n, which is 1 plus 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 1. Ultimately, it's just n. I've got n of them all together. I need those two sums. And then after a whole bunch of magic happens, I get a result of 2. Right? Hey, look, most painless Riemann sum we've ever done. Because all you have to do is just say some magic happens and then there's a number. If you're interested in the particulars of the magic, it's over here. But there's kind of a lot going on. It isn't like the worst Riemann sum that exists out there. Believe me, there are worse. But well, we're going to very, very quickly get beyond Riemann sums in our wanting to use these integrals. So let's just, say we looked at it for tradition's sake, and then never do one of these again. Because again, they get hairy. But for the most part, the detail that's involved in this particular Riemann sum is really just computing the sum of I from 1 to n and the sum of 1 from 1 to n. Or as it turns out, we'll be computing n from sum of n from 1 to n, which means it's n squared. N times. But cool, all right. That's all I want to do on Riemann sums. Let's go look at some other fun stuff. Properties of double integrals. Well, there's an average value calculation that we can do, which is pretty similar to the average value calculation we had back in Calc 1. Back then, an average value of some function is its integral divided by the length of the interval that we're integrating over. More generalizable, it is the integral of the function divided by the magnitude of its domain. Since our domain is an area, the magnitude of our domain will be an area. So 1 over the area times the integral of the function. Of course, it's going to be a double integral now because it's got multiple variables. And some other properties of double integrals. Most of the same stuff from singular integrals still apply. So there's the addition of functions or the addition of integrals. I can see here that I can just separate out addition in integrals, split it up into 2 separate integrals where I'm just summing the individual pieces. Instead of the total sum, I get that constants can be factored out of integrals, just like they can get factored out of sums. And the same idea still applies that if I have one function that's bigger than another function, then the integral of that first function will be bigger than the integral of that other function. Or rather, I should be saying the definite integrals there. Because once I start looking at indefinite integrals, then they're just functions, and there could be some other constant value that gets involved. But again, if I'm just looking at definite integrals, so over some fixed region R that I know, that same inequality is going to hold up. But the last couple of parts in this unit, interpreting some of these double integrals. Before we still, again, we're going to keep dancing around actually calculating one of these directly. And instead, kind of think about what these things represent geometrically. So I'm going to look for the double integral of 4dA, where my region is that circle. X squared plus y squared is less than or equal to 9. So that's a circle in the xy plane with a radius of 3. Probably you got that. The function that I'm integrating is 4, or try that again. More particularly, that's the function z equals 4. So that's just a plane, and it gives me an upper bound to be doing my integral over. If I sketch that region, which you can see I've sketched on the left, that ends up looking just like a cylinder, where I'm integrating in between the planes 0 and 4. Right, that's where the top and the bottom of my cylinder are. And I'm pretty sure I can calculate that volume. So let's give it a shot. So the double integral over R of 4dA. Remember that this is just a volume, because that's how we want to interpret these double integrals. There'll be some kind of a volume. Since a single integral was an area, a double integral will be a volume, probably. And our particular volume should be the height of our cylinder multiplied by the base of our cylinder. And here I'm going to write base with a capital B to indicate that the base is an area instead of just a length. But I'm pretty sure I know all that stuff. The height is 4. Right? I can come over here and look at this height right here. The height of my cylinder is 4. And the area of the base, well, it's a circle with the radius of 3. So pi r squared is going to be pi times 3 squared. 4 times 9 is 36 pi. So without actually needing to know how to directly compute any integrals yet, I can just evaluate an integral by looking at the volume of the shape that I've got going on. To do a few more examples like that, let's try this one. We're going to integrate over D now. So our region's going to be D instead of R, because D is the letter in the alphabet after C, and sometimes it's nice to do that. We can call our area whatever we want to. This time it's going to be D. So we're going to integrate the function d square root of 9 minus x squared minus y squared. D is the disk. X squared plus y squared is less than or equal to 9. So if I were to write this thing out, our function is z equals the square root of 9 minus x squared minus y squared, which notably is always greater than or equal to 0. A square root will always be greater than or equal to 0. I'd only get under that if I had a plus or minus involved, which this one does not provide to us. So it's just the positive square root. Meaning, if I square both sides and move all my variables to one side, I have x squared plus y squared plus z squared equals 9, with the particular caveat that z is greater than or equal to 0 from the same statement above, which means if I look at my equation, right, hopefully we recognize x squared plus y squared plus z squared. That's a sphere with a radius of 9 centered at the origin. So our shape is the top half of a sphere. And again, I think I can calculate that volume. So double integral over d of the square root of 9 minus x squared minus y squared dA is going to be a volume. Our particular volume is going to be 1/2 of 4/3 pi r cubed. 4/3 pi r cubed. That's going to be 3 cubed. And then I can simplify all those numbers to get something. 3 cubed over 3 is just 3 squared. 4 over 2 is just 2. 9 times 2 is 18. And a pi. So often when we're talking about half of a sphere, we'll just call it a hemisphere, as pointed out in the next example down, where we're going to be after the average height of a point on the hemisphere x squared plus y squared plus z squared equals 16, again with z greater than or equal to 0. The nice thing about taking these hemispheres, where z is greater than or equal to 0, is that I can then write that sphere as a function. Because typically spheres themselves wouldn't be functions, just like circles aren't functions, because at least they're not functions of x or functions of x and y, because they'll fail vertical line tests, because we'd hit both the top and the bottom half of the sphere. But if we only look at the top half of the sphere, then that part by itself is a function. So that's nice for us. So if we wanted the average height of that thing, we might be looking at something like this. The double integral over, well, let's use D again. This one didn't tell us what region to use, but we'll figure that out in a second. I need a function for height. But if we're in 3 space, the height is just the z variable. Z is going to be a function of x and y, but height in all 3 dimensions, the z-axis usually measures up and down. So the height of some point is just its z coordinate. So I want to integrate z. Again, it's a function of x and y. dA. If that's the integral of my height, and I want the average height, I should just divide that thing by the area. Right, because that was our average value calculation. So actually, I'm going to slide this over one more time and call this z average. Is that average height? So I can start putting a bunch of this stuff together. I just did an example where I looked at the double integral of a hemisphere, and I know it's just half the volume of that sphere, so I can probably just plug that bit in. First off, though, I'm going to need the area that I'm integrating over. Uh, if I'm looking at z greater than or equal to 0, my domain or my region D is going to be that sphere projected down into the xy plane, which will just be the circle x squared plus y squared equals 16. Alternatively, if I'm projecting into the xy plane, that is the plane z equals 0. So just plug in 0 for z and you get the equation of your domain. Long story short, that thing is a circle with a radius of 4, so 16 pi is its area. And I want to multiply that thing into 1/2 of 4/3 pi times r squared. R is, or nope, r cubed. Try again. Usually don't get the math wrong. 4 cubed. Once again, it's a sphere and only the top half of it. And then I can just simplify all of these numbers. So overall, what do we have? We have a pi in the top and bottom, so it'll cancel out. I've got 4 cubed over 16, which is 4 squared, so only one of those 4s is going to survive. You have another 4 up in the numerator, though, and a 2 in the denominator. So ultimately, I think that's just 8. If I keep track of all of my powers of 2, I think there are only 3 left over in the end, 1, 2, and 1, 4. And that 3 never went away. So 8/3. Which, as a fun little thing to point out here, that's 2/3 times 4. You can look that up later if you want to. One last example, and then we'll call ourselves done. Consider the disk given by x squared plus y squared is less than or equal to 25. On average, how far away is a point D from the origin? So we want an equation for distance. I'm going to start by writing down distance squared in terms of x and y, right? Where I ultimately want that thing to be a function. And it is, what is it? It's x minus 0 squared plus y minus 0 squared. I'm just in the plane, so I don't need the 3-dimensional distance formula. The 2-dimensional distance formula will be just fine. I'm writing this thing as away from the origin. So I'll, just plug in 0, 0 for the point I want to be looking at. So D as a function of x and y, don't want to forget that part, is just the square root of x squared plus y squared. And if we recall the stuff that we learned back in 12.6, which is our quadratic surfaces, we'd recognize this equation as that of a cone. So D is a cone. So we're going to look for an average value over here. D average should be something. It'll be the integral, double integral, over the region. D is a point this time, so I'll go back to using R for region of the distance formula of x and y, dA. And again, I know that D is going to be a cone. However, I can't just calculate the volume of the cone. Because if I do that double integral, remember this should be the area under the curve. So I'm really looking at the area that is underneath this cone. And if you just kind of think about what that shape's going to look like in your head, I know I'm right out of time, so I'm going to skip the picture real quick. But again, think about the way that that cone is going to work. The volume of a cone would tell you everything that's on the inside or everything that's above our surface. We want everything that's below it. So if we just drop down the sides of that cone right at the edge of our region, we'll find that we're really cutting a cone outside of a cylinder. Let's just imagine a cylinder with a height of 5 and cut the cone out of it. Meaning to get that volume or the volume of the integral, I really want the volume of a cylinder minus the volume of our cone. The cylinder should have an area, or a volume, excuse me, of 5 times 25 pi minus the volume of a cone, which is 1/3 base times height. So 1/3, 5 times 25 pi. And of course, I forgot to divide all this by the area. So let me just do that at the end. Divided by the area. Divide this whole thing by 25 pi to get an average value. And it's going to be 2/3 times 5. Which I'll leave that part as an exercise, but probably I think you can get there. Okay, cool. I know I'm over on time, so I'll end things here. So yeah, it's fall break. Don't come to class on Monday because I won't be here, and neither should you. But do have a good fall break. I will see you guys again on Wednesday. Okay, bye, 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 bye.